our paths from source to target. Given directed a cyclic graph of n nodes labeled from 0 to n minus 1, find all the possible paths from node 0 to node n minus 1 and return them in any order. The graph is is given as follows. Graph I is a list of all nodes you can visit from node I. Example, there is a directed edge from node I to node graph IG. So we can see this example visualized in this image. Example 1, we have the graph list here, and it shows the we have 3 paths here, and here, this and this. These are the paths, and it says we have 3 paths. We can go this way, 0, 1, 2, then 3, or we can go 0, 2, and 3. And this one is it's a larger graph with more complications passed through it. So it makes sense that there's much more to it than this. So this is a combination of this is a DFS graph traversal problem with backtracking usage. So let's make our result, which we'll put our final list in or output. let's make a helper DFS function. Let's call it dev DFS, put node and path. Let's go ahead and call that outside our function back up. No, DFS this time. DFS node is 0. We're going to start from 0. It says 0, and then our path will be 0 also. Let's put 0 in it. So we're starting from 0. So the node is 0 in the path. Path has 0 already in it. So let's put 0 inside the path. So now let's check. So if node is equals to the length of graph, let's call graph here minus 1. That's it. Minus 1. Let's take result. Then append append our path, and then copy it. So now we have that. So now let's make our let's visit neighbors. Visit neighboring nodes. So for neighbor neighbor and neighbor in graph. So the node that we're on, let's take path and then append neighbor, and then call the DFS input. Let's take hold on, neighbor. Let's oops, and then path. So we're going to apply the DFS on the neighboring path. Then so that will be hold on, path dot pop, so we can pop it off. So now let's take return result, and that seems to be it. It's a simple problem. Let's see if you have any syntax errors. That should work. Let's see if it does. And it's been accepted. It's an easy problem. Well, depends on your level, but it's a simple problem to understand if you understand backtracking. So our time complexity is a exponential, so it'll be 2 to the power n because exponential number of paths explored. Space complexity is also wait, it's n to O of n times 2 of n. Story of paths is exponential. And the length of the length of n. So let's submit to see if it's going to pass all cases. And it's been able to pass all cases. And that's it for this problem. It's a simple problem to understand. Once you understand backtracking and a simple concept, it's just simple concept of graphs.